Yeah, welcome everyone. So this is our last lecture for this course, and I conveniently have the result from, or the final, the final result from our previous lectures still at the board. So previously we discussed the question: do we need to quantize gravity, um, or can we just live with a semi-classical theory in which gravity remains classical? We have quantum matter living on a classical space-time. Um, yes, and what are the implications on the level of the Schrödinger equation? And we ended up with those two possibilities in the last lecture. So we either have the possibility where we say gravity, whatever quantum gravity is, for high energies, for low energies, we quantize gravity, we quantize the metric just like a field, like we know from quantum field theory. This is usually called perturbative quantum gravity. And we end up in the Schrödinger equation with a gravitational potential that looks just like the potential we know, for example, from electromagnetism. So this is just a mutual interaction between particles in a many-particle Schrödinger equation. And very different to that, we found a potential, a semi-classical potential that results in the Schrödinger equation for semi-classical gravity. We also had this earlier already and referred to this as the Schrödinger-Newton equation in the case of a single particle. So if we put n to 1 here, then we just find the equation that earlier we derived as the non-relativistic limit of the Klein-Gordon field, classical Klein-Gordon field on a classical space-time coupled to Einstein's equations. So what we have here is the potential that, if plugged into the Schrödinger equation, gives us an n-particle Schrödinger-Newton equation. And so today we want to ask the question, can we experimentally test how gravity behaves? Is this true, or is semi-classical gravity true? If you have a look at the lecture notes, I give you a lot of calculations and a lot of in-between steps. There you also see that the lecture notes are slightly longer, I think 10 pages. This is more if you're interested in the details of what I'm going to tell you today. If you're really interested in, okay, how do we end up with this equation, have a look at the lecture notes. You will find a lot more there than what I will tell you at the board today, because I want to focus in this lecture on the physical results and really on the basics. What do we want to do as an experimental test? What are we looking for in such an experiment? So I will skip a lot of the more technical things in the script, and I will only give you the equations that I consider really important to be understood. So have a look at the lecture notes if you're interested in the details. The first thing we want to do with these equations, and that means I'm already skipping the first 2 pages, I think, in the lecture notes. The first thing we want to do is, now we have this n-particle equation. We've seen the Schrödinger-Newton equation before, and we already know if we want to test gravity, we need a large mass somehow. Gravity depends on mass. The reason why we can safely ignore gravity in most realistic experiments is because gravity just doesn't play any role for the masses that we usually find in the lab. So obviously what we want to consider are massive systems. If we have such a massive system, it will always be a many-particle system. We will have to do experiments with molecules, nanoparticles, so the largest objects that we can still somehow get to show a quantum behavior. So first thing we want to do is somehow we want to look at this n-particle equation for a large number of particles, n. But we are interested in the behavior of one particle, of one system, of one molecule that somehow sticks together as a molecule. So we're interested in the center of mass motion of this this object. So what we want to do is we want to find a Schrödinger equation for the center of mass of a complex system of n particles which satisfy or which gravitationally interact according to those potentials. And so we don't really need to talk about quantum gravity right now much more, because we know how quantum gravity works. It works exactly, so at this level, it works exactly like what we know from electromagnetic interaction, for example. So this is just the Coulomb potential between two particles. If we have a single particle, there will not be any effect. Also, if you look at the center of mass of a single particle, this potential will perfectly separate, and it will only contribute to the relative wave function. So because you have the distance here between two particles, this potential will only appear as a relative potential in the interaction, in the internal interaction of your particle. It will not contribute at all to the center of mass motion of the particle. So the effect of this quantum gravity potential is zero for what we're looking at now. And the interesting thing is that for semi-classical gravity we will find that it is non-zero. So the first thing we do is we write this in center of mass coordinates. So we introduce a center of mass coordinate that we call capital R. We introduce relative coordinates, which are called Qi. And we split the wave function, so our total wave function, which here is called phi, so our phi n. That depends on all the particle coordinates, will be, I want to write as a product of the center of mass wave function, which I just called psi, of the coordinate r, and some relative wave function, which I call chi, which depends on the relative coordinates here. So we have we replace one coordinate by the center of mass coordinate, so we will have n-1 relative coordinates. And now we can insert this into our semi-classical potential, and what you will end up with is minus Gn. Now we still have one sum over particles, but you will see that you can replace the second sum, and you will simply have an integral over the center of mass coordinate and an integral over a second variable, which I call u. And then we have the center of mass wave function, psi of r prime, absolute value squared, times rho of u divided by, and now this distance here in the denominator becomes the center of mass position, r minus r prime, our integration variable, plus qi, the relative coordinate of the ith particle, minus u. And rho of u you find defined also in the script. Rho of u is essentially a function of the relative wave function. But if you look at it, what it really is just the mass density that is given by like the internal mass density of your object. So intuitively, the idea behind this is we have now in total we have a Schrödinger equation that contains electromagnetic interactions. that hold our particle together. Think of a molecule. So we have a molecule, and the atoms in the molecule are held together by electromagnetic forces. So these electromagnetic forces determine the shape of the molecule. We have some stationary state of the Schrödinger equation for those internal forces, and this internal shape, this internal wave function that comes out as the solution of these internal forces, defines a certain mass distribution that is given by this internal wave function. So chi, basically, I can just get from the Schrödinger equation without gravity, and it will give me a mass distribution. And now I can include gravity also here in the relative degrees of freedom, but there it's true, what is always true for gravity, that it's such a weak force that it just doesn't really change much. So the shape of the molecule will still remain the same even if I include internal gravitational forces. So this rho, this mass density, really is just the mass density of, or the mass distribution inside the particle we have. So rho of u would be the mass distribution of our molecule with respect to the center of mass of the molecule. So this appears here together with the wave function for the center of mass. So this is nice, but we have a problem here. We still have a qi here. So this is actually, and this is an exact result, right? So this is just replacing the coordinates. Then we get an exact equality of this potential, but we still have the center of mass. We still have the relative coordinate qi here in this potential, and we have to sum over all particles. And this actually makes this potential inseparable. So if we have the separation into center of mass and relative wave function, because of this type of interaction Hamiltonian, our Hamiltonian does not separate in center of mass and relative degrees of freedom. Our Hamiltonian will give us an entanglement between the two. So we actually, in principle, we would have to look at the full n-particle equation and solve the full n-particle equation. So what we can do without this gravitational potential, that we just say, well, we have the internal forces of our molecule that hold our molecule together, but we can ignore those and just look at the center of mass, which just solves the free Schrödinger equation. So we get the spreading of the center of mass according to the free Schrödinger equation. This we can no longer do here. We have a term that entangles the center of mass coordinate with the relative coordinates. But we keep in mind that gravity is very weak, and we can make an approximation in which the potential does separate. And this is very similar to what in nuclear physics or in atomic physics is known as the Born-Oppenheimer approximation. So if you remember from your atomic physics lectures, the assumption with the Born-Oppenheimer approximation is that you have the electrons and you have the nucleus in an atom. And in principle, you have to calculate all the mutual interactions of the nucleus with each of the electrons. So you have a very similar problem as here. But because the electrons are so much lighter than the nucleus, their motion is so much faster that you can effectively describe it as the nucleus just seeing a cloud of electrons. So you can average over all the electrons and just take the expectation value of their positions, and you find this electron cloud with which the nucleus is actually interacting. And the same you can do here if you take into account that whatever the electromagnetic forces or the other forces are that hold our molecule together, they will be so much stronger that these internal dynamics are so much faster in comparison to gravity, which is only very slowly reacting, that we can effectively just take the average of all these internal degrees of freedom. And only take the motion of the center of mass in this cloud that is given by all the internal motions. So what we do effectively is we take the expectation value of this potential in the relative wave function chi, and this gives us a potential that depends just on the center of mass coordinate. So yes, so if we take the expectation value with respect to the relative wave function, we find a semi-classical potential just of the center of mass variable, which has the following form. We can write it as minus g times an integral d3r prime, the center of mass wave function psi of r prime, absolute value squared, and then a function which I call I rho of r minus r prime. So this is just a convolution, the German word is Falltun, of the absolute value square of the wave function with this function I rho. And I should tell you, of course, what this function I is. And first define it. So I rho of d is a double integral and now of the mass density. Remember the mass density that is given by the relative wave function, rho of u. And then we have the mass density again, but now shifted by this difference d. And then I just have the distance u minus v. So, so what this is intuitively is the gravitational energy that I get if I take the mass distribution rho of u and I take a copy of the same mass distribution and I shift it by a distance d. Then the gravitational energy that I need to create this split by distance d between those two mass distributions, this is given by this function I rho. And and now with this potential we can write the Schrödinger equation for the center of mass, and this is now what we refer to as the Schrödinger-Newton equation for the center of mass. So we find that the total Schrödinger equation separates in relative motion, where the relative motion is dominated by the internal interactions, electromagnetic forces that just shape our molecule, and the center of mass, which again, remember, which would, without this self-gravitational term, without that semi-classical gravity, the center of mass would just follow a free Schrödinger equation, where you just have the momentum term, and now we have this potential in addition to that. So we have wave function that, strictly speaking, is a function of time and the center of mass coordinate. So the time derivative of this is minus h bar squared divided by 2 times the total mass of our system. Capital M is the sum of all the small masses of all particles. The Laplace operator with respect to the center of mass coordinate r. Plus this potential V semi-classical of r acting on the wave function. So this is now the equation we want to study. And first we can look at the case of a small system, or of a system that has quantum-like behavior, that has a wide wave function. So it's a particle-like system. So this would be the case. This would be the case where our mass distribution rho of u can be approximated as a delta function. So the particle itself, the molecule, is small with respect to the size of the wave function. Then we can approximate this rho of u by a delta function, and you see that we get for I rho, we just get the usual, so we just get 1 over absolute value of d here. And so just write this here. Rho of u would be delta function of u. Then our I rho just is 1 over the absolute value of d. And now we can go in here and we find that our potential is just the Schrödinger-Newton potential for a single particle, which we already had before. So, as expected, if we have a particle-like system, we find the single particle Schrödinger-Newton equation, but now not as an equation for a single particle, but now as the equation for a massive, for the center of mass of a complex system. So, as we would intuitively expect, we find the single particle Schrödinger-Newton equation also for large systems for their center of mass, but only in the case where the wave function is large enough so that we can ignore this internal mass distribution with this mass density rho. Now you know, of course, if we have massive systems, if we have large systems, then we usually have the opposite case. They are usually very well localized. The wave functions are very narrow, that's why they appear classical to us. So we can ask, what do we do in the opposite case? And what we can do in the opposite case is we can expand this function I rho. So we can go and do a Taylor expansion of this. We can say I rho of d is approximately I rho at 0 plus the gradient of I rho at 0 times d, plus we go up to second order. So the second order Taylor expansion term is 1/2 times the transpose vector d times the Hessian matrix with respect to I rho. If you remember from your analysis in higher dimensions courses, the second derivative for a multidimensional function is the Hessian matrix. Excuse me. So again, evaluated at 0 times d plus higher order terms. And the first thing to note is that this function I rho is actually symmetrical. So it doesn't matter what this mass distribution is. I rho always has the property that I go from d to minus d. I get the same. So I rho of minus d equals I rho of d. And because of this symmetry, the first order derivative at 0 vanishes. So this term does actually not appear. Now you also see why we need to go to second order, because this is just a constant. If we integrate with the wave function, this integral gives us 1. So this term just gives a constant potential. And the constant potential in the Schrödinger equation, just gives us a constant phase that doesn't matter in any observation. So this we can also ignore as an irrelevant term. So the lowest order relevant term actually comes from the second order derivative. And now we can go to a spherically symmetric distribution. So if our rho of u is actually just a rho that depends on the absolute value of u, then the Hessian matrix is diagonal. Let me just write it in the units that I want to have. I can write this as minus k divided by g. I just put the g in here for convenience. Times the identity matrix. So if we have a spherically symmetric mass density, which we want to now exclusively have a look at, then we find a diagonal Hessian matrix here. And you can plug this in. You will find, so basically we find d squared terms here. And now if you look at this equation, so d squared, so you will have r minus r prime squared here. So you will get terms that are r squared, and then just an integral over the wave function, which gives you a 1, so you will get an r squared potential here. Then you will have terms that are r times r prime. So again, the r just goes out of the integral. Now you have the r prime here integrated with the wave function, so this will give you an expectation value of r. And then you have the r prime square term, which will give you an expectation value of r squared. So, and if you take all of this together, then you end up with the Schrödinger equation again. And I write a one-dimensional Schrödinger equation now, which only depends on x, which we just pick out, randomly. So you will see you could go one step in between and write the Schrödinger equation, a three-dimensional Schrödinger equation first, and you will see that for the potential we get now with the approximations we made so far, you will find a Schrödinger equation that is separable in the three coordinates x, y, and z. So with that we can just focus on one of the three dimensions and write a one-dimensional Schrödinger equation. So we find a one-dimensional Schrödinger equation minus h bar squared divided by 2n. Plus, and now we have the following. We have, so I add something here that wasn't in the previous equation. I allow for a quadratic potential, for an external quadratic potential, with some constant k0. So this is just an external potential that we add. And then the coupling, then the potentials we get are k half times x minus expectation value x squared plus k half expectation value of x squared minus x expectation value squared. And this acting on psi of tx. So first of all, note that this is still a nonlinear Schrödinger equation. Okay, it doesn't look like it. It looks like a boring harmonic oscillator now. But you have these expectation values which depend on the wave function. So you would actually need the wave function to evaluate these expectation values. So because of this, this equation is still nonlinear in the wave function. Just the way of writing it in terms of the expectation values yeah, makes it look like a linear Schrödinger equation. So we have, so we have this equation, and now we want to ask what are the dynamics that follow from this equation. A convenient way, if you have such a harmonic oscillator-like equation, is to look at the equations for the expectation values, precisely for the first moments, so the expectation value of x and p, and for the second moments, so the expectation values of x squared, p squared, and the correlation x times p. So this we can do, and I just give you one example, and we calculate the expectation value, or the time derivative of the expectation value of x. So this is the expression we want to calculate now. So first we write this explicitly. This just means the time derivative of the integral of psi star of tx, x times psi of tx integrated over x. This is just the definition of the expectation value. And now I take the time derivative, so I get the time derivative acting on psi star and the time derivative on psi. So I have psi dot star x psi plus psi star x psi dot dx. Okay. And now I use the Schrödinger equation. So now I use the Schrödinger equation to calculate psi dot star and psi dot. And in order to do this, I call this, just for convenience, I don't call this potential V, but I actually call it h bar squared divided by 2m times V of t and x. Okay, this is just I get rid of the h bar and 2m here by making this choice. So I just take that out as a global factor. It doesn't change anything about the results. Just keep in mind that the V I write now is not really the potential. It's just the potential up to this constant. Yes. So using the Schrödinger equation, we then have, so I h bar divided by 2m, we now write just in front of our integral. And we find, so first we can write our psi dot prime as, so that's psi prime, second derivative, minus v times psi prime, and here for psi dot we will find that this is also psi double prime sorry, this has a global minus, so this is minus plus because of the complex conjugate, and here we have plus psi double prime minus v psi, and if I insert all of this, then I end up with minus psi star prime prime x psi plus psi star x psi double prime dx. And you see that in this case, for the position expectation values, we just have v and minus v here, so those two will just cancel. So this will be just a so psi star v psi and minus psi star v psi. So those just cancel. This is different if we have a momentum operator here, so because v is a function just of x and not of momentum, right? So if you would have an expectation value p here, then you have the derivative in the momentum operator not just acting on the wave function but also acting on the potential, and then you also get terms of the potential here. But for the x expectation value we don't have this. And now once we have this, the trick is basically just doing doing integration by parts to simplify this expression. The easiest you can do is just by integration by parts get all the derivatives from psi star onto psi, and the whole thing will simplify. Yeah, we can do this explicitly here. So I can do an integration by parts first for this term, and I actually do it for both. So yeah, let me just do this at the board. So if I do an integration by parts here, I get the boundary terms in principle, but I require that the wave function and all the derivatives of the wave function vanish at infinity. So because of that, I just get the integral term from partial integration. So I get a minus here, and now one of the derivatives actually goes to dx psi prime. And now I can integrate by parts again, or I can also do a partial integration of the second part, and I get this. And yes, and again, so I have when this derivative acts on x, I get IH bar divided by 2m. So if the derivative acts on x, then this just gives me a 1. So I find psi star prime psi minus psi star psi prime. And when the derivative acts on psi, I have, as for the potential, I have psi star prime x psi star prime x psi prime. So those two will cancel again and do not appear here. Yes, and now I can do one more partial integration with this one. So if I integrate by parts here, I have the derivative going from the psi star to the psi prime, giving me a minus here. And now I have just an action of the momentum operator that gives me this derivative. So I can write this together with this minus IH bar. I can just write this as so this is 2 times the same term, then that cancels this 2. So what I get here is I find that this is just the expectation value of the momentum operator divided by mass. So I have an equation for the time evolution of the expectation value for x, which is just expectation value of p divided by m. And I can do the same for all the other expectation values, and you will find all the calculations in the lecture notes in detail. So, for example, what I get for the time derivative of p is, and now the potential enters. But the potential enters in such a way that so if I take the first order, the expectation value here, then you will see that the terms here with x and expectation values of x will just cancel each other. And what actually survives is just the k0 term here. So what we have is minus k0 times the expectation value of x. And I can put those two equations together into one second order derivative. So I can take the second time derivative here and find just a harmonic oscillator equation. I find that the second order time derivative of x is minus omega 0 squared times x with frequency omega 0 being k0 divided by m squared root. So the expectation values just satisfy a harmonic oscillator equation with the frequency just given by whatever my external potential is. So if I have no external potential, then that will just be free motion of the particle. If I have an external potential, if I have my molecule or whatever my complex particle is in a harmonic potential, then it will just, the expectation values will just satisfy the same equation they would satisfy if there wasn't any self-gravity. So self-gravity has no effect on these first moments. So now I can do the same for the second moments, for the expectation values of x squared, p squared, and p times x. And again, you will find the calculations in the lecture notes, but the important result is that now you can write the dynamics of those second moments as a again as a differential equation, a third order differential equation. So the third order time derivative, and now the easiest expression is to actually take the variance, so the difference of x squared expectation value minus x expectation value squared. And you will find that this again just satisfies the differential equation. So this is minus 4 omega squared times the first order time derivative times the same expression x squared minus expectation value x squared. And this is well known from the study of harmonic oscillators. So with this knowledge you can actually create what is called a squeezed state. So if you think of the harmonic oscillator, usually in quantum mechanics you study stationary states of the harmonic oscillator. So those are the states that correspond to a classical oscillator that's just sitting there at rest. So if you would look at the classical motion, the motion of the expectation values, you would just find the expectation, you would just find the oscillator sitting there if it's in the ground state. Then you have states where you can take this ground state and you can off-center the whole ground state, and then you will have an oscillation of the ground state, but it will keep its shape. It will stay in this stationary wave function, and this whole wave function will just oscillate with some frequency. So this would be what we call a coherent ground state. So this is a state where the expectation values p and x oscillate with some frequency, but this width, this expression, the variance, the width of the wave function is still a constant. So that's the zero solution to this equation. And now you can have what we call a squeezed state, where you actually make this ground state, the Gaussian function, a bit wider or a bit narrower. And what such a state will do is it doesn't just oscillate as a whole, it doesn't just oscillate the center of the wave function, but also the width of the wave function, so it will have some breathing motion. And this is the solution of this equation. So this equation gives you exactly this breathing of the wave function. So you have a Gaussian that gets wider and narrower with some frequency omega here. And now comes the crucial part. So in the standard harmonic oscillator, if we don't have the semi-classical gravity potential, this omega is exactly the same as the omega that determines the internal motion. So those two motions will be in phase. But this is no longer true here. If you now evaluate these expectation values, you find that this omega is actually given as the square root of k0 plus k divided by n. Okay? So, or I can also write it as square root of omega 0 squared plus k divided by n. So the self-gravitational interaction that we find gives a shift of this frequency, gives us an offset of this frequency. So the internal oscillation is now at a different frequency than the oscillation of the system as a whole. And this is something that can be in principle observed in an experiment. So we can measure, we can observe how the wave function behaves, and we can see if the oscillation of the wave function itself happens at a different frequency than the oscillation of the center of the wave function. So in order to see if we can really observe this realistically, we need to now discuss what would be some numerical values here that would actually make this work. And the first thing we need to discuss, so we have this constant k, which is somehow associated to this function I rho that we had, but we haven't really discussed in detail what exactly this k is. And remember, the function I rho depends on the internal mass distribution, on the mass density rho. So the first thing you can do is you can just think of a spherical distribution of a homogeneous sphere. So we have a homogeneous spherical mass density. Rho is constant within some sphere and 0 outside of the sphere. And in this case, so homogeneous sphere. In this case, one can actually find an analytic solution for this function I rho, and one finds that the constant k is simply gm squared divided by the radius of the sphere cubed. So m is the total mass of our system, r is the radius of our homogeneous sphere. So I have this function. But this is not a very realistic model for what we have in a real experiment. Actually, most of the time, or one can get a significantly better effect if one takes into account that the way a real system is built up, if I have a chunk of some material, say the silicium nanoparticle, or a little micro-diamond or something, which would be typical systems that you would find in experiments, then the way I have to think about this is more like I have, say, for simplicity, I have a spherical particle. It actually doesn't really matter so much what the shape is, but let's say I have a spherical particle, and inside that I have the atoms. So if we have a crystal, then we would just have a regular structure of atoms here. But again, it's not really important whether it's a crystal structure or whether they are just like, it could also be glass or whatever. But the point is that we have the distribution of the atoms here. If you take, for example, the Debye model for a crystal, those atoms internally will have some Gaussian distribution, some Gaussian mass distribution. Remember again, the mass density rho comes from the internal wave function. So if we solve the Schrödinger equation, we get the internal wave function, we can in principle calculate this mass distribution rho. Of course, in practice, we need to make approximations, but a good approximation is that there is a Gaussian distribution with some width, which we call sigma. And and the whole sphere here is supposed to have the radius r. And then in this case, so for crystal, then we find that our I rho we can write approximately as the term 6m squared divided by 5r. This is basically the energy of the whole sphere, if I offset it by a certain distance. This is like the constant, this is the zeroth order term. And remember, this does not really contribute to our Schrödinger equation, so we don't really care about this all that much. Now the important part is that the correction to this that comes from basically the offset of these atoms inside the crystal, we can write as the total mass of our system times the mass of one atom divided by d, so I rho as a function of d, times the Gauss error function of d divided by square root 2 times this parameter sigma, which is the localization of the atoms. And again, we can, from this I rho, we can calculate this constant k, and we find that k is a prefactor square root 2 divided by pi, and then it is g times the total mass times the mass of one atom divided by 3 sigma cubed. And with this we can now calculate our omega here, and we find, because we have a k divided by m here, so k divided by m, the correction to our omega, is now a quantity that depends only on the mass of a single atom and on this localization width of the atoms inside the crystal. So both of those are material properties. So we see that the effect actually, if we are beyond a certain scale, so if our center of mass wave function is narrow enough to actually probe these distances inside the atom, then the effect really only depends on the material that we have, and not so much on, or not anymore at all, on the total mass of the system or the size or the shape. So we need to find a good choice of material, and you will find, for example, in the lecture notes, you find a table which shows that this correction of the frequency, so square root k divided by m, is something like 0.05 inverse seconds for silicon, or the best material. The best material is actually osmium. Osmium, not just because it has it has the highest possible density, but mainly because the localization sigma here is smallest for osmium. And for osmium, you will get a whole order of magnitude better, so you will find 0.5 inverse seconds. So this is what we have to work with. So this is some frequency that is just given to us by nature. There isn't really much we can do to get this better. Right? So this is important to notice. Like, increasing the mass of our whole system doesn't really help. We need somehow a material with better parameters, but we don't know of any material that has better parameters, like that has a better localization of the atoms, or cannot make the mass of a single atom arbitrarily large. So this is the best we can do. So of the order of 1 hertz, basically, as a frequency. And now, in order to observe an effect, in order to observe this difference between omega 0 and omega, we want to make sure that this frequency difference is not too small with comparison to omega 0. So we want omega 0 to be close to this. So we want omega 0 to be not too much distinct from this frequency correction in order to get a significant effect. But it's important to keep in mind, I already mentioned that, we made this up. The whole calculation we made is in this approximation where we expand I rho to second order in D. And this expansion is only correct if the wave function is relatively small with comparison to the length scale where we have a significant change of our mass distribution. So we want a wave function, a center of mass wave function, that is actually smaller than this length scale sigma here. And now if you think of the ground state of the harmonic oscillator, this means that sigma should be larger, or at least not much smaller than the width of the center of the harmonic oscillator ground state, which is h bar divided by m omega 0. So this would be the ground state in the external potential with frequency omega 0 that we have given. And if we take those two criteria together, then we find that we need a certain mass in order to achieve this. So basically, we want to make our omega 0 small, but we want to also keep this number small. So if omega 0 is small, we need to make the mass large enough to get a relevant effect here. So if we plug both of those, if we stick both of those together, then we find that our mass must be larger than h bar divided by sigma squared square root k divided by m. And remember, so there is an m here, but this is exactly this material dependent property. And we can calculate this now for these values, and I think I used the value for osmium here. So what you find is that you need a mass that is about 10 to the 16 atomic mass units. So the mass of about 10 to the 16 hydrogen atoms. So basically we know now which experiment we have to do. We need to have a mass that large, we need to get it trapped in a frequency that is around 1 Hertz, and we need to observe the dynamics of squeezed states. And this is something that is challenging, but it's not ridiculously far away from what people are doing. These masses are actually, they appear large in comparison. I told you in an earlier lecture, I think, that about 10 to the 5 atomic mass units is what people use in interferometry experiments. But you can have much higher masses in optomechanics experiments. So in experiments where you have a particle sitting in a trap, and people do actually experiments with masses that are around this order already, like 10 to the 14 atomic mass units. The difficult part is to really get them to have a quantum behavior, but this is not impossible. This is something that is quite feasible, and then you need to get, and this is kind of the bit more tricky part, you need to get to these frequencies which are quite low. So the frequencies that are usually used are closer to like kilohertz or even megahertz frequencies. So it is a relatively weak trap that needs to be used here. And so this is kind of the challenging part. But again, so this is something that's like order of 10 years maybe of work away, and not something that is like the scale of building a particle accelerator the size of the solar system. So what we discussed in the first part of the lecture was testing this Schrödinger-Newton equation, testing this specific semi-classical interaction that we got from replacing in Einstein's equations the stress energy tensor by the expectation value of the stress energy tensor. And there is a second type of experiment that I want to discuss, which is a very recent proposal, actually, only like 2 or 3 years old. Sorry, 4 years, I think, old now. That tries to approach the whole idea of testing if gravity is quantized from a slightly different perspective. So the idea here is the following. We know that if we have quantum interactions, we get entanglement. If we have two particles and they interact through a quantum force, electromagnetic force, for example, then the state of the one particle gets entangled with the state of the other particle. So if you have a force that depends on the position of both particles, like for example, the electromagnetic, the Coulomb interaction between two charges. And the idea is that only a quantum interaction, only a quantized field is able to, in this way, generate entanglement between two separate particles. So I will discuss this now for the specific example of semi-classical gravity, of the potential that we used the whole time. But the nice thing about this is that this is actually a way more general test. So for what we discussed previously, the experiment to test the semi-classical potential. If we do the experiment and we find the semi-classical interaction, this would be great, of course, because then we would know, well, gravity is completely different from other fields. Gravity actually interacts in this semi-classical way. But if we do the experiment and we find, well, the standard Schrödinger equation without the self-gravity potential works just fine, and then we know semi-classical gravity is wrong. But we still don't have definitive proof that gravity must be quantized. We would just rule out the most straightforward model for this. But we could have some different mechanism in which still space-time is classical, but we don't. But we don't see the specific semi-classical potential. So the idea here is really, if we assume that the characteristic feature of a quantum interaction is that it can actually transmit entanglement, and we kind of use this as the definition of what we mean by quantum, then we can really test whether the quantumness is there. So this is not a test for non-quantumness, as the test of the Schrödinger-Newton equation would be, but this is really looking for quantum effects, looking for entanglement. And in order to discuss the idea, I want to go back to our potentials that we had again for quantum gravity and semi-classical gravity, but now I write them for just two particles. So our potential for quantum gravity is simply the interaction between the two particles, so minus gn squared divided by the difference R1 minus R2. And the semi-classical potential, on the other hand, you remember, had self-interactions too. That was what we discussed. Previously. What was our idea to test the Schrödinger-Newton equation for a single particle? So every particle sees its own gravitational potential. So we get a self-interaction of the first particle and a self-interaction of the second particle. But the important thing for us now is not the self-interaction, but it's also that the mutual interaction between the particles also looks different. If we take our semi-classical potential, what we actually find is that there are two terms. There is one where we have the position of the first particle, and the first particle sees the expectation value of the second particle, the wave function of the second particle, and we have a potential for the second particle, whose gravitational potential comes from the wave function of the first particle. So this also looks completely different if we look at the interaction between two particles. And this is now exactly the point, that this is a potential of two coordinates. So this is really a non-local interaction term that depends on the position of both particles. Whereas, and will give us entanglement, whereas this are two separate terms in the potential. These are two separate potentials that are local potentials. They only depend on the one coordinate here, this one only on R1, and this one only on R2, and on a classical property, the expectation value, which is an observable quantity. And so such types of interactions are also in quantum physics are also referred to as local operations and classical communication, or in short, LOC. So this means I could get this effect by just locally measuring the expectation values of R2 and communicating through a classical channel, it's like calling and on the phone and telling what the measurement results are. So communicating through a classical channel the result of this measurement, and then using this classical result as the source for a local potential at position R1. So there is no quantum non-locality in this potential. And this is why there will be no entanglement from such an interaction. So now, if we want to exploit this, and for this I have to show you the picture. So if we want to look at this, and so here you see the experiment that was proposed in 2017. So the experiment you have is we take two particles with spin 1/2. We send each of them through a Stein-Gerlach device, so basically an inhomogeneous magnetic field, in which they are split up into a superposition state. So the first particle is split up in the state left with spin up and right with spin down, and the same for the second particle. And now those two experiments are close enough together that if the left particle is in the right trajectory, so right one, so this scenario, the particle 1 in the right state will be close enough to particle 2 in the left state, so that those two can actually interact through gravity. So they will feel their gravitational potential. And for simplicity of the calculation, we ignore the gravitational potentials between all the others. We just assume that the separation between the others is significantly large, so we don't have to take into account that there is a gravitational potential between them. So we start with the state, so 0, which is just a product state of I don't write the left and right here, so if you look at the lecture notes, it's always left up, right down, but I just write up, understanding that up means the up state that's in the left position. So spin up of the first particle plus spin down for the first particle. And now tensor product, or separable state, up for the second plus down for the second. So I also leave all normalization factors out here. And this I can now write as one long product, as one long sum. So I have, I can write this as up, which means spin 1 left, up, spin 2 left up, and the same way plus up down, plus down up, plus down down. So this is the initial state that I have, and now what happens is that, remember when we discussed the cow experiment, if we have those two parts of the wave function, where we have the left state in, let me switch again here. So if we have the particle 1 in the right spin down state and particle 2 in the spin up state, then they are close enough together to feel their gravitational interaction. So the down up state here, this one will actually interact gravitationally. And as you remember from when we discussed the cow experiment, such a weak gravitational force basically just gives us a phase change, so at the lowest order. So we get some e to the I phi phase effect here. If we now look at, leave this. If we now look at the state after some time t, where this phase is basically given by the gravitational interaction between the two, g, first particle mass, second particle mass, times the time, sorry I call this tau here, times the time they have next to each other, divided by h bar and divided by the distance between down and up, which I call delta x. So delta x is just the distance, again if I switch, is the distance between the right state for particle 1 and the left state for particle 2. And now we can ask what happens in the semi-classical case. So this is the quantum situation, and now I can look at the semi-classical situation. And in the semi-classical situation, from this potential, you see that basically the left, or the particle 1, doesn't care which state particle 2 is in. Particle 1 just cares about the average, or the expectation value of the whole superposition. So particle 1 sees the same gravitational field for the second one, regardless of which state it is in, and the same the other way around. So particle 1 basically sees the second particle as if half the mass was in the one position and half the mass was in the other position, no matter which part of the superposition we are actually in. So this is just the peculiar behavior that this semi-classical potential has. So it's very weird looking from the perspective of quantum mechanics, but if you remember again how we got it as a result of the semi-classical Einstein equations and from the assumption of having a classical spacetime, it makes sense in principle. And if we do this, then we see that basically every time we have a spin down in the first state, and every time we have a spin up in the second state, we always get a phase that is half this phase, because we have half the mass interacting for the second particle. So so we get half the phase here. We get no phase here. we also get half the phase here for the spin down. And here we get half a phase and half a phase, so we get the same phase as we got in the quantum phase, in the quantum case. So the difference between the semi-classical and the quantum case comes from those two phases. But because of this distance, of this difference, we can also still write this as a separable state. So this is actually the same as up plus e to the I phi half down tensor e to the I phi half up plus down. Okay. So whereas this one becomes inseparable, we have entanglement, this one remains separable. And now the question from the perspective of an experiment is how can we actually observe this? How can we find this entanglement? And for this we need what is called an entanglement witness. So we want to have some observable quantity that shows that if there is entanglement, can take values that it cannot take without entanglement. So values that can only be explained by there being entanglement. And such an entanglement witness can be defined by measuring the following. We, on the one hand, we make a bunch of measurements and always measure the outcome where we measure the spin of the first particle in the x basis, so in the basis that is in the x, that we measure the spin in x direction, and we measure for the second particle the spin in z direction, and we take the expectation value over a whole bunch of measurements. And then we make another series of measurements in which we measure the spin in y direction for both particles. And now we can calculate these expectation values, and we find that in the quantum case, that this expectation value gives us one half e to the I phi minus 1. And this expectation value gives us exactly the same, 1/2 e to the I phi minus 1. And we can do the same calculation with the semi-classical state that we found. And we find that this one is e to the I phi half e to the I phi minus 1. And this one is actually 0 for the semi-classical case. So there is no such correlation of the spins in y direction. So if we calculate this entanglement witness, then we find that in the quantum case we have our W being between 0 and 2, and in the semi-classical case W can only take values between 0 and 1. So this one can at the most, for a phase of minus pi, this would be minus 2, so the whole value would be minus 1. Same here, this would be minus 1, so we would have an absolute value of minus 2, so plus 2. Whereas here we can only get, so we can at the best get a 1 out of here, and then we have the 0 here, so we cannot get more than 1 here for the semi-classical case. So if we can measure this quantity in a bunch of observations, and we find any value that's larger than 1, then we know we must have had entanglement here. So this way we can witness this entanglement. Now the difficult part is kind of, we need to repeat this experiment many times under the same conditions. So in the paper from which I showed you the figure originally, there is a suggestion for concrete scenarios. So the difficulty is that the distance between the two particles, when they have the closest approach, must be large enough that there are no other forces that are more dominant than gravity. The most important other forces are the Casimir-Polder forces, which are based on the Casimir effect, so an effect from the quantum electrodynamic vacuum. And the requirement that those forces are much smaller than the gravitational forces means you have to be at least something like a couple of 100 micrometers apart. So this is the distance you need. And then you can calculate what mass you would need to get a relevant phase shift, and you find masses that are 10 to the 14 kilograms, 10 to the minus 14, sorry, kilograms. So those are the orders of magnitudes with which we have to do. The distance, the closest approach of the two particles, about 100 micrometers, and the mass of the particles about 10 to the minus 14 kilograms. And those are not completely ridiculous masses. It's a very challenging experiment, but that would in principle be possible. The tough thing is, so you want to detect this gravitational interaction. If you just look at these numbers and ask, well, how strong is this gravitational force? You see, there is actually only a significant phase change because we divide by h bar, which is a very small number. But the gravitational potential that you get from these parameters is the same, or is a similar gravitational potential as you would get if you have a size of a centimeter size object that's a kilometer away. So even a small thing like a bird flying past the window of your lab or something will have a much stronger gravitational field. So the way you can get around this is you have the whole experiment freely falling. Then the equivalence principle tells you that everything outside your lab you can ignore because the whole system is free falling. But you still need to make sure that all the relative accelerations that you have between your particle and the experiment are so small, because you need to repeat the experiment multiple times. If you have any acceleration there, it will just spoil the effect completely and get rid of all entanglement. So you need to have a super good resolution with respect of accelerations. We actually need accelerations that are smaller or of the order of picometers per second squared. So again, those are the accelerations between the experimental setup and the particles themselves. And this is very challenging actually, and on Earth, so that such numbers are usually not achieved. But one could think of doing an experiment in space in zero gravity, for example. So a very elaborate satellite mission for that could do something like that. So the experiment seems more challenging than what we discussed about Schwittler-Newton, but it has the huge advantage that it really would confirm quantization of gravity rather than just exclude one specific alternative model. Okay, so the main message to take away from both those things is that so the main message to take away is that while it's while it's difficult to test real quantum gravity effects at the Planck scale, and there we would need a huge effort and gigantic particle accelerators or something like that. The question, do we need to quantize gravity or not, might actually be one that we can answer in an experiment. So yes, and with this I'm also finishing not just this lecture but the whole course. And yeah, I hope you had fun and you learned something a little bit about the issues and possible solutions around gravity, that gravity is not just, that gravity with quantum mechanics does not just become a problem when we talk about Planck scale, Planck length, black holes, or the universe, but that already, if we're talking about quantum systems in the lab, it's a very interesting question to ask, okay, what about gravity? How do we include gravity in those systems? And what do we really know about how gravity acts in these systems? So with this, goodbye, and thank you for all your attention throughout all these lectures.